Hi, my name is Chloe. For this video presentation, I'll be presenting on Chapter 25, Amines. An overview for this chapter consists of four main parts, which are amines and its properties, preparation of amines, reaction of amines, and reaction of diazonium salts. First, let us look into amines and its properties. Amines are compounds which have a nitrogen atom bonded to three atoms and has a non-bonded lone pair. Therefore, it is sp3 hybridized and the shape is trigonal pyramidal. When amine is bonded with three different alkyl groups and an electron pair, the nitrogen atom is the stereogenic center. However, chirality of the amine nitrogen is ignored, as two of the enantiomers interconvert rapidly with one another. For nomenclature, the systematic name of amines is given by locating the longest carbon chain bonded to amine nitrogen. The E ending of the alkyl chain is changed to amine. There are other specific names that are used based on the structure, such as aniline and pyrimidine. Third is physical properties. For the boiling point of amines, tertiary amines have lower boiling points than primary and secondary amines. This is because tertiary amines have no NH bond to form hydrogen bonding. Primary and secondary amines also show higher boiling points than ethers but lower boiling points than alcohols. For solubility of amines, all amines are soluble in organic solvent. Only amines having less than or equal 5 carbons are soluble in water. Next, for the spectroscopy properties, amines that have odd numbers of N atoms will give an odd molecular ion in their mass spectra. For IR spectra, primary amines will show 2 NH peaks at the range of 3300 to 3500 per centimeter, whereas secondary amines will only show 1 NH peak at 3300 to 3500 per centimeter. For NMR spectra in 1H NMR, NH signal will appear between 0.5 to 5 pm, whereas 13C NMR shows that the carbon bonded to the N atom absorbed at 30 to 50 ppm. Lastly, we'll look into the basicity of amines. Amines are stronger bases and nucleophiles than other neutral organic compounds. As the basicity decreases across the row, we can see that nitrogen is the most basic compared to oxygen and fluorine. There are also a few factors that determine amine basicity. First is inductive effect. This explains about the electron donating effect of alkyl group attached to the N atom of amines. Therefore, amines that have R groups are more basic than NHR. Resonance effects explain the delocalizing of the lone pair on N atom, which will decrease its basicity. Therefore, amides that can delocalize its N lone pair are less basic than amine. Aromaticity describes the condition of nitrogen lone pair in the aromatic pi system. If the lone pair is part of the pi system, the lone pair will be delocalized in the ring, making it less basic. Hybridization effects describe that amine's basicity is based on the %S character. A lone pair which is in an sp3 hybrid orbital will have less %S character than the lone pair in an sp2 hybrid orbital. Therefore, the less tightly the lone pair is held, and the stronger is the base. Now, I will talk about the reactions we have in this chapter. First is the preparation of amines. There are four types of reactions used to prepare amines. The first one is direct nucleophilic substitution. This reaction is an accentual reaction of an alkyl halide with amines or ammonia. Next is Gabriel synthesis. Primary amines are synthesized by using ptylamide as the starting material. Amines can also be synthesized using reductive methods. Nitrile compounds and nitriles are reduced to primary amines, while primary, secondary, and tertiary amides can be reduced to primary, secondary, and tertiary amines. Aldehyde and ketones can also undergo reductive amination to form primary, secondary, and tertiary amines. Next, we will look into the reaction of amines. Amines can act as a base to react with acid. Nucleophilic addition of aldehydes and ketones with primary and secondary amines produce ethene and enamine respectively. Nucleophilic substitution of acid, chloride, and anhydride with NH3, primary amines and secondary amines can yield primary, secondary, and tertiary amide respectively. Hoffman elimination is a reaction that converts amine into alkene. NH2 is a strong base, therefore it has to be converted to quaternary ammonium salt, which is a better leaving group. The reaction uses CH3I in excess, followed by Ag2O and heat. This reaction follows E2 mechanism of elimination. Lastly, primary and secondary amines can react with nitrous acid to form alkyl diazonomer salt and N-nitrosamine respectively. Nitrous acid is produced when NaNO2 react with HCl. The final part of the reaction in this chapter is the reaction of aryl diazonomer salts. Aryl diazonomer salts are useful intermediates that can be used to synthesize various products. It can perform substitution reaction as N2 is a good leaving group. It can react with water to form a phenol. It reacts with copper chloride or copper bromide to form aryl chloride or aryl bromide. It reacts with fluoroboric acid, HBF4, to form aryl fluoride, and reacts with sodium or potassium iodide to form aryl iodide. To form black benzene, the aryl diazonomer salts react with hypofluorous acid, H3PO2. Benzoyl nitrile can also be synthesized by reacting the aryl diazonomer salt with copper 1 cyanide. On top of substitution reaction, aryl diazonomer salts can undergo coupling reactions with aromatic compounds that has a strong electron donating group. Examples of strong electron donating group are NH2 and OH group. The coupling reaction is an electrophilic aromatic substitution with diazonomer salt, serving as an electrophile. This reaction results in the formation of an azo compound. Now I will talk a little bit more on Gabriel synthesis. Gabriel synthesis is a reaction used to synthesize primary amines. The starting material for this reaction are ptylamide and alkyl halide. Gabriel synthesis begins with the deprotonation of ptylamide to form a resonance stabilized anion, which will serve as a nucleophile for the next step. The deprotonation takes place by using a base like potassium hydroxide. The next step is the nucleophilic substitution, where the nucleophile reacts with the unhindered alkyl halide in an SN2 reaction to form a substitution product, which is the alkylated imide. The final step is the hydrolysis of alkylated imide with aqueous base to form primary amines and dicarboxylate byproduct. One of the industrial applications of Gabriel synthesis is found in coumarin-based fluorescent probe for hydrazine detection. In a research paper, it reported the design of fluorescent hydrazine probe. Based on scheme 1 shown in the diagram, probe 1 was synthesized by reacting O-ptylyl anhydride to the coumarin derivatives through Gabriel synthesis. And when hydrazine reacts with probe 1 shown in scheme 2, the fluorescent compound 1B is renewed. The reaction shown in scheme 2 describes that one nitrogen atom of hydrazine attacked the carbonyl of ptylyl anhydride in probe 1, destroying the amide bond. Then another N atom of hydrazine attacked another carbonyl in probe 1. Therefore, when hydrazine attacked the probe 1, a fluorescent compound is synthesized. Therefore, the design probe based on Gabriel synthesis is able to detect the presence of hydrazine. Next reaction I'll be sharing is diazotization. It is a reaction of the formation of diazonomer salts. The starting material used in this reaction are primary alkylamines and aryl amines with nitrous acid. By using NaNO2 and HCl, primary alkylamines or aryl amines can be used to synthesize the alkyl or aryl diazonomer salt. This reaction starts with the formation of nitrosonium ion. NaNO2 reacts with HCl to form nitrous acid. The nitrous acid reacts with HCl and the removal of water will form a nitrosonium ion. The next step is the formation of an N-nitrosamine. The nucleophilic attack of the primary amine on the nitrosonium ion and the deprotonation by chloride ion forms an N-nitrosamine. The following steps involve the reaction of N-nitrosamine with HCl. After several steps of proton transfer and the loss of water, the diazonomer salt is formed. The industrial application of diazonomer salt can be seen in the fabrication of biomembranes-like films on carbon electrodes to detect hydrogen peroxide. The first step of this method is the modification of glassy carbon electrode GCE with aldehyde groups. Scheme 1 shows the electrochemical reduction from p-nitrobenzaldehyde, then the formation of diazonomer salts, and lastly electrochemical reduction to form the aldehyde groups. In scheme 2, the aldehyde groups were reacted with alkane thiol, and lastly the dideosyl dimethyl ammonium bromide DDAB was casted on modified GCE. This biomembrane film was further modified by incorporating myoglobin and big gold nanoparticles, and the biosensor is used for the detection of hydrogen peroxide. In this chapter, we discuss about the properties of amines, such as the physical properties like boiling points and solubility, spectroscopic properties of IR, NMR, and mass spectra, and also the basicity of amine. The preparation of amine is introduced in a few reactions like direct nucleophilic substitution, reduction method, Gabor synthesis, and reductive amination. Last but not least, the reaction of amines such as reaction as a base, nucleophilic substitution, and nucleophilic addition, Hoffman elimination reaction with nitrous acid, and the substitution reaction of diazonium salts. Amine is an important class of compound that are useful in the industry for various purposes, especially as reaction intermediates. These are the references for this presentation. That's all from me. Thank you.